All right, hi everybody. I see it's 3:32. So in the interest of time, we're gonna go ahead and get started. Welcome to the Graduate Student Lightning Talk Department Seminar. Today we're gonna have 3 graduate students giving short lightning talks about their research. We'll do about a 15 or so minute talk and then leave about 5 minutes after each talk for questions. And you can either mute and ask or type the question in the chat, and we'll keep an eye on that. I also want to mention that we have another seminar 1 week from today. I know usually we're every other week, but we do have a speaker next week, and that is Asaya Kiseka. And so please join us again this time next week for that. And so I guess without further ado, I'll go ahead and turn it over to Leanna Leverich, who's going to be our first speaker. And Leanna is a student working with Dan Kaiser.
All right. Okay. Well, hi, everybody, and thanks for tuning in today. It's exciting to get to see a lot of people logging into the department. Like Kelly said, I'm Leanna. I am a third-year PhD student, and I'm working with Dan Kaiser and Seth Nave in agronomy. And today I'm going to share a little bit about what I'm working on more on the soil side of things. And this is work on assessing the soil mineralogical properties and chemical properties and the impacts that that has on corn potassium and fertilizer recommendations. This is kind of one of the newer projects that I'm working on. So I just completed the first year of data collection for that. So I'm kind of excited to share it with you. So as we all know, cropping is big in the United States. We have about 254 million acres of farmland in the United States. And a lot of that is made up by corn production. So 90 million acres of the 250 some million that we have is all planted to corn. So corn is kind of king in this country. And 95% of that corn production makes up all of the total feed, grain production, and use. With that, we have some essential nutrients that we are all really familiar with. We know NPK, nitrogen, phosphorus, potassium, as well as our micronutrients and macronutrients. And many of us are really familiar with the primary plant essential nutrients for crop production, especially nitrogen and phosphorus, where we have a lot of work done because of their potential to contribute to pollution. However, potassium tends to be a little bit overlooked. Whoops. And potassium, even though it doesn't have any major environmental effects that we know of, it is a limited resource. It is a mined nutrient, and over-application is very costly to growers, and it is something that they would like to optimize. So our focus here is to look at potassium and how do we optimize potassium fertilizer for growers. Of course, if you don't apply enough potassium, we see major yield hits. So we have slowed down growth of the plant, chlorosis of the leaves, wilting. Basically, it's a major hit to the yield for the grower, so an economic penalty. So where do we start with potassium? Potassium all starts with the soil. So potassium supply to the crop is mediated by the soil. It's controlled primarily by the mineral quantity of the soil. So in general soil textbooks, we often see figures like 95% and 5%, where 95% of the potassium in soils is thought to be contained in the 2-to-1 clay mineral fraction, and the other 5% is available for plant uptake. So already here, we're hinting that clay mineralogy is going to play a role. So if we look at our potassium cycle here, we see our inputs such as plant residues, mineral fertilizer, animal manure, and then our outputs, of course, crop harvest, runoff and erosion, and leaching. But where we're really focusing here is the soil aspect here. So like I said, we have the soil solution K, which makes up about 5%. And then we have our mineral fractions making up about 95%. So the mineral fraction that is stable, which we might call mineral K, it is locked up in the actual mineral itself. So the only way to access that K is for that mineral to weather. Then we have our fixed K, and that is K that is held in between two layers of a clay mineral. This is somewhat accessible, but not readily available. It releases more slowly. And then we have our exchangeable K, which is K that is on the exchange sites of the outsides of clay minerals that will readily desorb and adsorb from the soil surface into solution. Looking a little more closely at our clay types. So we have 3 major clay types here, and these will be important for our experiment too. We have kaolinite, which is considered a 1-to-1 clay, mica or illite, which is 2-to-1, and smectites, also vermiculates, and 2-to-1 clays. So kaolinites are 1-to-1, meaning that they have 1 octahedral sheet and 1 tetrahedral sheet, and this makes up a layer. Whereas 2-to-1s have 2 tetrahedral sheets and 1 octahedral sheet, making up 1 layer. Now, what I want to touch on the most here is the mica versus the smectite, and I know this is review for some of us, but mica tends to fix K. So the space between this inner layer space between these 2 layers fits the potassium ions pretty perfectly. The size is right, and then the charges on these sheets is amiable for that potassium ion. And so micas or illites are very likely to fix potassium or hold it tightly in that inner layer. Whereas smectites, they have a lot more space in their inner layers, and they have ions kind of flowing more freely in and out. I shouldn't say freely, but they're more likely to move in and out of the inner layer, along with water and other cations such as magnesium or calcium. So potassium can certainly be caught up in this inner layer, but it's not going to fix in the same way that we see it in the illites. So considering the mineralogy and the effects that this has on potassium, we can also think about how our soil tests, how we test for soil K. So just like every soil test, we have methods that we use to prepare the soil before we conduct an analysis on the quantity or the proportion or the concentration of a mineral or a element. And what's interesting about potassium is that it reacts a little, or you tend to get a little bit different results depending on how you prepare the samples. So the literature points to moist samples and testing those for potassium versus dry versus air dried. And dry analysis, when you dry those soils and those minerals down, what happens in illites is that the layers tend to curl. And as they curl, they open up and they seem to release some of that inner layer K. Versus in smectites, you might drive, they find that you tend to be driving the water out of the clay mineral. And when that water is driven out, it leaves the cations that are there, including potassium, and they may become fixed or kind of bound between those 2 layers. Now, why does this matter? It matters because this directly shows us that mineralogy does influence K, and how we measure K is directly influenced by the soil mineralogy. However, states, they can use whatever test that they want, and there are different places around the US that use moist versus air dry versus dry. And what really matters for choosing the soil analysis is calibration and correlation. So depending on what soil analysis the state uses, maybe they use a few, as long as they are correlating that and calibrating that with yield data, that is what's going to lead to our K recommendations. Now, in North Dakota, they've started or they've conducted a similar study to what we are looking at here in Minnesota, where they are trying to use clay mineralogy to modify potassium fertilizer recommendations. And what they did is they sampled in each county, I believe twice, and then interpolated to make a map of the general mineral types to try and modify their potassium recommendations. And so that leads us to our question, can we use mineralogy and other underlying maps such as bedrock geology and surface geology to improve the mineralogy maps, and consider CEC and pH to improve our potassium recommendations? So our objectives here are to determine whether soil clay species can be utilized to provide more precise estimates of K critical levels, to determine if the soil CEC and soil pH should be considered in making K fertilizer guidelines, and to estimate soil K weathering capacity of soils with varying CEC for the improvement of recommendations for K fertilization. And I'm not going to get into 2 or 3 because we're mostly talking about mineralogy today. So I'll just focus on that piece. So our methodology, looking at Minnesota, we had a number of K response trials. And what I mean by a K response trial is we apply a range of rates from 0 to 160. In some instances, maybe it was more treatments, but this is the model we used for this past year. 5 different rates spread across the field, replicated 5 times. And this is in a farmer field to capture the yield response to potassium rate. And this was conducted across the state of Minnesota this past year at about 8 sites. And Dan luckily has a lot of K response data information from throughout the rest of the state. So the goal is for us to try and capture that K response and the different mineralogy throughout the state to modify our recommendations. So after those field trials were conducted, we would take a control plot, so something that a plot that was not receiving any fertilizer, and we sent that in for a X-ray diffraction analysis. And the X-ray diffraction analysis gives us a rough estimation of the different abundances of different clay minerals. So this would be an example of XRD reading, the output that we might get, and these different peaks indicate the relative abundances of different minerals. And this would be a sample of some of the data that we received where we get relative abundances of smectite, illite, kaolinite, and chlorite. So just looking at some pretty basic trends that I can see in the data thus far. So looking at our database of K, what we have currently, given the historical yield trials and this past year's yield trials, we can look at the differences between the moist analysis K concentration and the dry analysis. And we see that it's pretty tight along this line, but there are some discrepancies maybe up here in this area where we see spread from the line as you're getting higher K concentrations. And if we look at this considering the mineral fraction, we see the illites or the micas, that kind of one big class, and we can look at the smectites. And the smectites, and while these might be outlier points, they're quite high. There's few of them. They do kind of follow that trend that we see in the literature, that smectate dominated soils, that when they are dried, they may actually fix the potassium, so leading to lower dry analysis numbers while having higher moist analysis numbers. So that kind of follows the trend that we might be seeing here that's also in the literature. So this is, I'll walk you through this. This is just trying to look at relationships between our level of potassium, our moist sample analysis, versus our different types of clay minerals. So we have smectites, illites, kaolites, and chlorite. So first, looking at just the spread that we have in the data in our potassium levels You can see here that in smectites, we tend to have the higher levels of potassium in this data set versus illites ranging on the lower end. So already here, we're seeing kind of an inverse relationship, and that's actually very clear when you look at smectite versus illite. You just see this very clear inverse relationship between smectite and illite. And so that might help us to see, okay, there's a clear trend here. Where can we modify recommendations, given that we can see this trend? We also see these trends between kaolinite and chlorite. It's a very clear trend. You see a trend as well between illite and kaolinite. And also smectite and kaolinite has that inverse relationship. So these are all things that we can use as hints as to what minerals are related to what and how we can modify recommendations, what minerals are going to be important in modifying. As we look at the spread of yield, we kind of see the same relationship that we did to the level of potassium, the greater spread here in the smectite of yield with high yielding levels and also low, whereas in the illite, it's in the lower amounts of illite that we see the bigger spread, and so on. We see this same relationship. Now, okay, I'll hurry up a little bit because we're getting close to time, but here's our relative yield relationship to potassium concentration, and this is what we would use for correlation and calibration typically with soil tests. So just looking at our illite versus our smectite, we can see that smectite has a pretty big range. We've got higher testing higher amounts of smectite in a lot of our soil or a lot of our samples across the board here. But what we think may be very important here is the ratio. So what we want to get at is looking at the amount of smectite to the amount of illite. And looking at this relationship, we can try and put a breaking point or a break curve where we see the ratio might be higher versus lower. And so this is the general goal, is to see if we can use these ratios to create response curves for this. So a response curve is something that we're looking for is a quadratic here, fit to the data, and where we can optimize this for one ratio versus another. So smectite to illite, can we optimize that amount? So conclusions, yes, there are relationships between dominant mineralogy and soil test K analysis, and preliminary exploration of the data indicates that there is a potential to improve our K recommendations using mineralogy. And with that, I'll thank you, and I'll take any questions if we have a minute or two.
Okay, thanks, Leanna. Does anyone have any questions? I don't see any in the chat yet.
I can ask a quick question. This is Carl. Hi, Leanna.
Hi.
Just wondering, I know that Wisconsin has kind of used this approach for a while, and whether you've looked to see what their relationships are. We're pretty close to Wisconsin, so I'm just wondering if you've looked over there to see how their relationships have worked, and if they're using the same clay ratios or something different. It's
interesting that you bring that up. I didn't know that Wisconsin was modifying based on mineralogy.
Well, I think they've been doing it for a long time. I do know that I've seen their potassium recommendations. It's in yeah, it seems to be based on mineralogy or cation exchange, something. I just brought it up.
Exchange, I think, and also like coarse versus fine. I think that I believe that they modify based on like sand, and maybe if you have higher quartz amounts, I think, EC level. I'll definitely look into that. Thanks, Carl.
Yeah, see what the other thing is, I think they also use a weird extractant. I think they use the Bray extractant to do potassium, so it's
interesting.
A little different, but I just thought, look, just see what they're doing with their recommendations.
Awesome. Thank you, Carl.
All right, any other quick questions? All right, thanks again, Leanna. We'll move on now to Heidi Reitmeyer, and she is a grad student working with Lindsay Peace.
Right, thank you. All right. How's the slide looking? Okay.
Looks good.
We're good. Okay, so let's see. All right, thank you, and good afternoon, everyone. I'm Heidi Reitmeyer, as was introduced, and I'm pleased to be presenting to you today on a phosphorus index of Minnesota agricultural nutrient management for this lightning talk opportunity. It's good to see such a good turnout today from the department. So I'm a soils researcher and master's student with Dr. Lindsay Pease, assistant professor and extension specialist in the Department of Soil, Water, and Climate at the Defense College of the U of M. And we are both located at the Northwest Research and Outreach Center. This presentation will be about the updates that will be made with the Minnesota Phosphorus Index, or MNPI, that is currently available based on the data that I have collected and analyzed. So to preface this topic, you may have heard of this, most likely, that the hypoxia that is occurring in the Gulf of Mexico is caused by nutrients from agricultural fields across the Midwest, especially. And those nutrients are dominated by nitrogen and phosphorus. I will be focusing on phosphorus for this presentation. So as you can see, all these waterways across the Midwest collect toward the Mississippi River and then flow down to the Gulf of Mexico. And these rivers carry with them all these nutrients that are concerning, including phosphorus. So that is what we'll be focusing on, is phosphorus loss risk management, because this problem can be mitigated by phosphorus loss risk management strategies. And one way to do that is with a nutrient index, such as the Minnesota Phosphorus Index. So this index is one way to assess farm management practices for their phosphorus loss risk. So here's an introduction to the MNPI 2.0 that will be developed in the near future based on this existing index. So this index has not been updated since the year 2006. And we have new understanding of phosphorus dynamics in the literature since that year. New software will be developed by someone in our department with user-friendly features and will incorporate new Minnesota agricultural data that I have collected and analyzed for my thesis project. So the data requested from across the state of Minnesota came from these sources listed across here, such as the Minnesota Agricultural Water Resource Center, the Minnesota Department of Agriculture, the University of Minnesota, of course, as well as the Discovery Farms of Minnesota, all currently active entities that we were able to collect data from for analysis. And then among other online nutrient databases that we could access, these were grouped by Minnesota region and statistically analyzed for trends, including farm management data and phosphorus loss correlations that we could make based on that management data. So the data came from these Minnesota points on the map here, and they are color-coded on the right. So red indicates Discovery Farms, and as you can see on the list here, yellow is for Root River, coral is for Wilkin County, purple is for Lamberton, and then teal is for Waseca, Minnesota. Here, as you can see on the map, all these data points were sourced for data collection needs and further analysis. And then, so just an overview of how this current software program works. So the current MNPI looks like this when you go into the program. You would manually enter for each crop year your manure and fertilizer your synthetic fertilizer data, your soil test data, all tillage data, and anhydrous ammonia if there was any spring tillage, crop planted, cover after planting, and then a crop yield. Once you are done entering all your data, you automatically get a phosphorus loss risk assessment at the lower right-hand side of your screen. There, here it's shown in red because the data hasn't been entered yet, but that's what you get at the end of your calculation. So as you can see here, this average risk includes sediment delivery and other forms of phosphorus that could be in that phosphorus risk index calculation. And so that's just an overview of how this works. You just enter in manually each record from your farm records to get your average phosphorus loss risk. And then here's an example of what I was able to do with the current MNPI software with 3 of the fields at the Northwest Rock here where I'm currently working across about 30 years of data. So as you can see here, you can see that field 8, has the highest phosphorus loss risk, followed by field 1 and then field 5. Based, across those 30 years, you can see the trends for those 3 fields and how they differ from one another. And so, based on this calculation that I had done, we could say that field 8 is the most concerning and the one that we want to pay the most attention to because it is more of a phosphorus hotspot, so to speak, for us to look at. So there is an example of what the current MNPI index can do for you. And then just some graphs I'll be sharing here of some preliminary data results from when we're comparing these variables with the MNPI risk categories to see how well this model is working for us. So here's a box and whisker plot showing Discovery Farms runoff data versus MNPI risk category data. You can see how runoff was distributed across those risk categories. And the very low and low having larger distributions here, as you can see, as compared with the medium category. And then as you can see here, I have a one-way analysis of runoff by Minnesota region. So there was a statistical difference between Southwest Minnesota and Northwest Minnesota here. As you can see, based on its highlighted p-value, which is quite low. And then a difference between Southern Minnesota and Northwestern Minnesota here. So that is just something that we have noticed here across these regions. And then the Discovery Farms data here versus MNPI risk category for precipitation. Let's see, very low had the largest distribution, then low and lastly medium. And then looking at the differences across the Minnesota regions here, we see the largest differences between the southern parts of the state of Minnesota and the northern, as per these highlighted very low p-values, and then Northwest Minnesota and Central Minnesota with that type of value shown here as well at the lower right. So, okay, so total suspended solids yield, or TSS yield in pounds per acre by MNPI risk category shown here. As you can see, very low had the most data distribution, followed by low and medium. What was interesting to find as well was how total suspended solids can be quite large in their distribution and yet be associated with a very low MNPI risk category. So looking at a one-way analysis again here, we see a similar trend between southern Minnesota and northwestern Minnesota, and then between northwest Minnesota and central Minnesota for those p-values showing those statistical differences across those Minnesota regions for TSS yield. So you can get the sense of the pattern here. Okay, total phosphorus yield. Total phosphorus yield, okay, versus MNPI risk category. We do see something that we would expect here. The very low is showing up as a lower distribution than the low here, and I don't think medium had much data, so that's a bit odd. But so that one looks a little off, but the very low and the low look as we would expect them to based on their total phosphorus data distributions versus their MNPI risk categories. Looking at the one-way analysis here again, we see a similar trend between those same regions of the state of Minnesota, showing those differences in TP yield. So that one seemed to be, predicted as we would expect for the most part. And then, so DOP yield or dissolved orthophosphate yield looks somewhat as you would expect, but not quite. So the very low is lower than the low, but then the low is quite high in distribution according to this graph. And it doesn't look like what we would expect. We'd expect more of a staircase appearance. We always expect that staircase appearance, between very low, low, and medium. Here we don't really see that. So that is an interesting point to find. And here is a one-way analysis again with similar trends with those graphs of the state here and those p-values in particulate P. Now, let's see. Yeah, particulate P looks more like what we would expect as compared with the dissolved phosphorus. It has a nicer staircase effect here with the MNPI risk categories between the very low, low, and medium. Particulate P seems to be better predicted by the MNPI model than DOP here, which is very interesting. I have a theory about that, and I'm researching that phenomenon, so stay tuned. And then, let's see, sorry, the slides keep, yeah, and then just a couple graphs here from, Southwest Minnesota from these last 2 years here showing, total phosphorus yield across these regions that are having the highest TP yield as compared with the other Minnesota regions here on this graph. And also is shown by precipitation and its variation across the state here. Waseca seems to have the most precipitation in southern Minnesota as compared with other locations across the state from this recent data. So, I will transition here into the findings so far. So the current MNPI program seems to overlook high soil test phosphorus or SDP levels. We had many high SDP levels across the regions that did not show up in the MNPI risk calculator. Also, management practices might skew P problems according to the model. So if you were to change your management practices in the program, the P loss scale would not change very much. In the calculator, change in P loss may only change slightly. For example, even after changing cover after planting to greater than 20% for everything in your crop records. So we thought that was something to improve on, just that level of nuance and sensitivity of the model for the future going forward. Overall, P loss may be over underestimated at times based on my findings here, and as the MNPI may not be currently sensitive enough, as I said, to cover all these farm practices that are being inputted into the program. So recommendations, some recommendations we have at this point. Based on our prior list of improvement areas, P loss could be predicted more accurately in the future with fewer subjective human errors. Based on more objective input, we can incorporate from pre-existing databases to automatically calculate your data for you. So things such as, soil type, where you are located in the state, etc., could help you determine your P loss risk a little more automatically and perhaps we would think accurately at some point. So just, some ideas. Key software upgrades will incorporate updated knowledge of P loss as well as added user friendliness overall. So. All right, I would like to thank my advisor, Dr. Lindsay Pease, for being my advisor on this project. I would also like to thank Dario Canelon, our software developer, for the new MNPI updates that will be happening. And then finally, Peyton, she's our undergraduate student assistant who has helped with the data work that went into this project. And that's all I have. So thank you for listening. And let me know if you have any questions after this.
Great, thank you, Heidi. We do have 4 or 5 minutes for questions, if there are any out there.
So, hey, Heidi, thanks. That was really interesting. I just wonder if you could summarize some of the differences between the soils, the slopes, and the management practices at the Discovery Farm sites, so we could have a better understanding of how they differ from one another.
Yeah. So, yeah, I do. Let's see. They tended to be, lower slopes. I would say a few of them were, higher slopes, but usually more flatland, I would say, as I was processing this data. And then I tended to see like clay loam soils in the data, low to medium organic matter, as well as let's see, the other thing was like calcareous too was a point that was common among these sites. That's how I would summarize these Minnesota Discovery Farm sites for their soil types overall.
And what about the management practices?
Management practices. So let's see, there'd be about half the sites I think had tile drainage, for example. We had a lot of, I guess, well, we had more tile data, I think, than surface data. That was one thing. And then, let's see, I'm just thinking back to the data sets. Yeah, tillage was something that was, usually there was chisel plow tillage in the spring, fall, or both, but sometimes there'd be, sometimes, once in a while you'd see strip till or some sort of conservation tillage, but that wasn't the norm across the state. So just trying to think of some other farm management practices. We had the usual crops too, with a few unique crops. So like your usual corn, wheat, sugar beets were more in the Northwest region, so those were not common across the state overall. But and then soil organic matter tended to be, between, well, now I'm getting to some other data that was in the MNPI, but yeah, I mean, probably what you'd expect, for Minnesota management practices. So what farmers typically do around here, that's kind of what I was seeing in the data too. I hope that helps. It wasn't surprising. I'll say that
Okay,
as I was going through the data. Yep.
Yeah, I think the model wasn't really intended to estimate phosphorus loss in tile drains, but I guess what you were showing us was the data for the surface, where you have soluble runoff and particulate losses.
Mm-hmm. Mm-hmm. Yep.
Is there a big difference between the previous model and the one that you're using now? What are the big differences that in the current one?
So, well, the one that we're in the process of developing, it's still it's in the process of being developed. So it's just too early to say. Unfortunately, I wish I could share more concrete updates, but some of the suggestions that I had mentioned will be definitely considered as we're updating the model and the program. So yeah, one of the big things is just we hope to automate, if there's any sort of calculating, like cover after planting, instead of trying to calculate that percentage, this new software should be able to do that for you, or your location, if it'll be more automatic about where you're located, where that site data is coming from. It could pull from if it could just pull that data from somewhere more automatically.
So is it just more user-friendly type things, or is there something? I thought at one time I heard that you were So the original one used Russell 2, and that you were going to a different program for looking at losses. Is that true, or?
Yeah, and I should have said that. But Russell is the one that's in the current, the one that I was using.
And it's different now, or is it going to be the same?
I think it's just. Yeah, the Russell's the revised one, and I'm sure it's different now. But that wasn't in the one that I was. That's not in the one that I had downloaded and used for this for the model testing.
Okay.
I'm not sure what it. I don't know like offhand what it is. I think it is different. I just don't know the name.
Is there a timeline for getting this out then, or?
Timeline. We want to get this. I would think, there isn't like a hard timeline.
Okay.
I'll be honest, there isn't a hard timeline. We're just, chipping away on it as fellow scientists.
Okay.
But this is, within the next year, I think we'll make a lot of progress within this upcoming year. Through 2021, it should have a lot of progress and be, fleshed out. Yep.
Thanks.
Mm-hmm.
Okay, thank you, Heidi. I think we should move on to our final speaker, and that is GP Singh, and he is a grad student working with Vasu Sharma.
Thanks for the introduction, Kelly. Can you see my screen?
Yep, we can see it.
Thank you. So, hello everyone. I am GP, and I'm advised by Dr. Vasudha Sharma. And today I'm going to talk about my research. We are conducting a study in central Minnesota to study the impacts of different irrigation management strategies on corn yield and nitrate leaching. So first of all, in central Minnesota, due to coarse soil structure, we have really low available water storage. And as you can see in this figure, we have a high concentration of points in this region that have low available water storage, and which is even less than 4 inches. So with this, it becomes essential to irrigate the crop to obtain ideal yields for corn. And you can see that there are a lot of irrigation permits being issued in this region. And with this irrigation comes the problem of nitrate leaching. So the US EPA standard for the nitrate concentration in drinking water is 10 milligrams per liter. But as you can see in this region, there are a lot of private drinking wells that have nitrate concentrations beyond that limit. So basically, the objective of this study is to compare those irrigation scheduling methods and study their impact on corn yield and nitrate leaching, such that we can somehow reduce the irrigation-induced nitrate leaching without impacting the corn yield. So this study is being conducted at 2 locations in central Minnesota. One of them is Sand Plain Research Farm Becker, and the other being Rosholt Farm in Westport, Minnesota. So these regions receive almost 30 inches or 76 centimeter of annual precipitation. And these sites have really coarse textured soils with more than 80% of sand. So that allows very little water to get stored in this region. So in first 4 feet or 120 centimeters of soil depth, we not even have 10 centimeters of available water storage. So these are the irrigation scheduling methods that we are studying. First, soil moisture monitoring using soil moisture sensors. ET-based checkbook method, online ET-based irrigation management assistant tool, IMA, and EPIC crop growth model. So before we go into studying these methods, let's have a look on an approach that two of these methods use. So the water balance approach. So this approach is basically, it's based on law of conservation of mass. So if we consider this soil water plant system, the total input to the system or the total inflow to the system comes from irrigation and rain, and the total outflow from the system is due to evapotranspiration, runoff, and deep percolation. So the change in the soil water storage can be calculated through the difference of total inflow to the system and the total outflow from the system. So the first method, ET-based checkbook method, uses this approach to calculate the change in soil water storage based upon the difference in total inflow to the system, which is due to precipitation and irrigation, and total outflow from the system, which is due to crop evapotranspiration and water losses. So the calculation for crop evapotranspiration is done through daily reference evapotranspiration and crop coefficients for the crop. So the daily reference evapotranspiration comes from weather parameters, and Jensen-Hayes equation is used. So solar radiation and temperature are the weather parameters that are used in this calculation. And the crop coefficient curves developed for Cont for North Dakota are used. So this is the spreadsheet that we are using for checkbook method. So in this spreadsheet, you can see that different columns represent weather parameters such as daily maximum temperature and effective rainfall. So we have to input these parameters in this spreadsheet, and this spreadsheet, we take these parameters from local weather station data, and this spreadsheet would give you the soil water deficit based on which we can conduct irrigation scheduling. So this is the second method that we are studying. This is online ET-based irrigation management assistant tool. It uses exactly the same approach as the checkbook method, the water balance approach. The only difference lies in crop evapotranspiration calculation. So here the daily reference evapotranspiration comes from Penman-Monteith equation, which uses two additional weather parameters, which are wind speed and humidity, apart from solar radiation and temperature. And the crop coefficients in this method come from ASCE EWRI Manual 70. So let's have a look at the online interface of this method. And so this is the main screen of the tool. And from this part, I can select any of the plantings that I have already set up into the system. So for example, if I select Becker irrigation methods, and I can see the details of it and see whether irrigation is recommended or not. Also, I can look at the field water balance, or just to know that how much time is left for the next irrigation. So this is the third method, soil moisture monitoring using soil moisture sensors. So here we are changing gears. This method is very different from the previous two methods. So the previous two methods indirectly calculated the change in soil water based upon the water balance method or weather approach. So this method calculates the change directly from field measurements. So we are using neutron moisture meter to conduct those field measurements, and the field measurements would give you volumetric water content. Once we have the volumetric water content, we can calculate the soil water deficit from it, and irrigation is triggered whenever the soil water deficit reaches a level of maximum allowable depletion. And this maximum allowable depletion is kept from 40 to 60% of available water holding capacity of the soil, and it depends upon the crop stage and crop species. So along with this irrigation scheduling study, we are also conducting another experiment in which we are comparing different soil moisture sensors. So we have collected data across the growing season, and we are trying to find out that which sensors can be the best for farmers. But I'm not going into soil moisture sensors a lot today. And let's get back to irrigation scheduling. So this is the fourth irrigation scheduling method, that is EPIC crop growth model. This is a field scale mathematical model that simulates yield, water, and N balance. This model functions at a daily time step, but it can go on till years, and it has a lot of input parameters. It has more than 200 input parameters, but we are not using all of them. We don't have to use all of them. So this is a example input window from the model, and there are a lot of input parameters, but for example, in our case, we are just interested in some of them, such as soil water lower limit, soil water upper limit, and what type of irrigation method we are using, and what is the cropping system. So we can just input those parameters which are of interest to us, and then we can obtain the desired output. So for example, in our case, the desired output is irrigation scheduling, which is the amount and timing of irrigation. So with all these irrigation methods, we conducted this study last year. That was the first year of the study, and irrigation amounts that were recommended by all these irrigation scheduling methods were applied at the two sites. And it was a really wet year. We received almost 632 mm of rainfall and 538 millimeters of rainfall throughout the growing season at both sites. And it is important to note that the Irrigation Management Assistant tool gave really low irrigation recommendations at the second site. It didn't recommend any irrigation throughout the growing season. So when we look at the seasonal crop evapotranspiration from last year, it is interesting to find that the Irrigation Management Assistant tool, irrigation scheduling method, had the lowest crop evapotranspiration. And this is the method that also required the minimum irrigation, that recommended the minimum irrigation. And at one of the sites, its recommendations were significantly lower than other treatments. So we also collect plant samples throughout the growing season at different crop stages, just to check whether if there is any difference in the N uptake by crop due to the difference in these scheduling methods. So, but we see that there is no significant difference at any of the crop stages at both the sites between these scheduling methods. So we got really interesting results for nitrate leaching, and it's important to note that maximum nitrate leaching occurred during the period when we apply irrigation. And at the second site, overall, we didn't apply much irrigation because it was not recommended. And we didn't apply much irrigation throughout the season, and we don't get much nitrate leaching at this site. And the checkbook method of irrigation scheduling had a significantly high nitrate leaching. And it's very interesting to know that the checkbook method was the one that had the highest irrigation recommendation at that site. So nitrate leaching is following the trends of irrigation. So we were glad to look at the yield results, because some of the treatments, such as the irrigation management assistant tool, gave really low irrigation recommendations, but that didn't affect yield at all. So both the sites had good yields, and there was no significant difference in the yield. And in fact, highest yield was obtained under the EPIC model-based irrigation scheduling. And it is important to note that the EPIC model is not the one that got the highest irrigation. So we conducted this research again in the second growing season, 2020, with these irrigation amounts. And we are expecting to see some more interesting results. For now, we have the N uptake at various crop growth stages. And as expected, we don't see any difference in N uptake for different treatments. So these are some conclusions from the first year of the study. The checkbook method based irrigation scheduling produced a significantly high nitrate-N leaching at 95% confidence interval. The IMA based irrigation scheduling resulted in significantly low crop evapotranspiration. Both corn yield and N uptake, they were not significantly affected by irrigation scheduling method used, and highest grain yield was in fact obtained under EPIC crop growth model, which is not the one that got highest irrigation. And IMA tool based irrigation scheduling produced highest yield per unit water used, and it also gave us the minimum nitrate leaching. So with that, I would like to thank the funding agencies, Minnesota Department of Agriculture and Minnesota Corn Research and Promotion Council, and also our department field crew for helping us in field operations, and also Dr. Mullah and his team for helping us with the EPIC crop growth model. So that's all, and I would love to answer any questions if time permits. Otherwise, you can reach me out at syncgp@umn.edu. Thank you.
All right, great. Thank you, GP. Are there any questions?
Just a quick question. What was the nitrogen rate that was used? I assume it was the same at both sites, or?
Yes, the nitrogen rate was kept constant across all the treatments and both the sites. It was 240 per acre.
What, 240 pounds per acre? Or
yes.
Kilos or pounds?
Pounds.
Pounds, okay. All right. Yeah, that's fairly high rate. I was surprised your uptakes weren't, was the uptake total above ground, the nitrogen uptake, or was that just grain, or what was that?
So it was the combined uptake.
Okay, stover and grain. Okay, thank you.
Would you expect these results to change at lower nitrogen levels? Maybe maybe excessive?
Yeah, they might change at lower nitrate levels, but we are conducting this research at the recommendations which are in best management practices, because we are interested to find out the best irrigation scheduling method for farming in central Minnesota. So we are keeping other variables at constant and at best management practices.
Any last questions? All right, if not, I want to thank our 3 speakers again today, Leanna, Heidi, and GP. And thank all of you for joining us. And don't forget, next week we will have another seminar this time, and that will be Isaiah Kiseka from UC Davis. So hope to see you all then.
Thank you.
Yep, thanks again.